Percentiles are a measure of relative standing. So that means where data values are relative to each other. So there are 99 percentiles, and it partitions the data into 100 groups. So a value, and here's the notation, a value like P60 is the 60th percentile, and the 60th percentile means that 40% of the data are larger than P60 and 60% of the data are smaller than this value. So the 60th percentile gives a number which represents that value for which 60% of the data is smaller than that value and 40% of the data is larger than that value. The 99th percentile is a value where 99% of the data is smaller than that value and 1% of the data is larger than that value. In terms of graphic displays, when you make an ogive, this graph, which is a graph of, what is that? Those are ordered pairs, and its cumulative frequency is used to do that. So you can use an ogive to estimate percentile values, and that is something that we do in the Excel video on making an ogive. So there's two algorithms, well actually there's a number of algorithms to find percentiles, and we'll look at two particular algorithms. So if we want to find the percentile rank corresponding to a given value, a particular value in the data set, you have to sort the data set and count the number of values that are smaller than that data value, add 0.5, divide by n, the sample size, and multiply by 100%. Okay, so that would give the percentile rank corresponding to a particular value. On a different note, Q1, 2, and 3, which we've seen before and come up when you do the one variable stats in your calculator, Q1, 2, and 3 are the 25th, 50th, and 75th percentiles. These are called the quartiles. Quartiles are very common percentiles, but other percentiles are used as well. And you can note that the 50th percentile, which is Q2, that's the median. Well, on the other hand, if we are given a different question, we want to find the data value that corresponds to a particular percentile rank. Here's the algorithm to do that. The first thing you would do is sort the data, and then you have to compute this index value. The index value is the value in the ordered set where the percentile of interest would lie. So for example, if you wanted the 30th percentile for the data, it would be 30 over 100, or 0.3 times n, where n is the sample size. Now, when you compute this index value, that value will either be a whole number or not a whole number. If it's not a whole number, you take the next larger integer. Even if the index value is, say, some whole number plus 0.001, you would still use the next larger integer. This is not rounding. If the index value is a whole number, then you take an average of that value plus the next value over 2 from the ordered set. Again, this is an index value. We'll look at examples of that in a few minutes. Just a note, IQR stands for interquartile range, and it's the difference between the third and first quartile. The interquartile range gives us a way to look at values that are potential outliers or are considered outliers using something called a resistant measure. Resistant meaning doesn't use the mean, because we know the mean is highly influenced by extreme values. So the bounds for detecting a potential outlier, the lower bound would be Q1, that's the 25th percentile, minus 1.5 times the IQR, and the upper bound for a potential outlier is Q3 plus 1.5 IQR. Okay, so try this. So try this prior to listening to the video and see how far you can get, and then we'll go through it. So you should pause now and then listen again in a few minutes. Okay, so we have 16 scores from a 20-point test, and those scores are here. Now you can see these scores are not ordered, right? They're in a random order. So our first task is to find the value that corresponds to the 60th percentile. Okay, so we want to find a particular value, which value in the data set corresponds to the 60th percentile. Okay, so what we need to do according to our algorithm, and that's the the algorithm that's on the top of page 20 in your notes, we'll have to first sort the data, then compute the index value for the data value of interest in the sorted set, and then decide from there. We'll go from there to see which value that corresponds to. So again, our first task is to sort the data. So assuming you've entered this data in list 1, under the list functions and under math, you can sort. Sort A means sort ascending, so that will sort from smallest to largest. So if you first sort the data, right, then our next task is to calculate the index value for the 60th percentile. So how do we do that? Well, there's 16 scores, so it's going to be n times p over 100. So it's 16 times 60 over 100, which is 16 times 0.6. So that's 9.6. So 9.6 is clearly not a whole number. So if it's not a whole number, we're going to use x10 from the ordered set. So the 10th value from the ordered set, if you look at these ordered, and you should sort them and put them in list 1, the 10th value from the ordered set is 13. So 13 corresponds to the 60th percentile. The next question is, what's the percentile rank of 6? In other words, the value of 6 corresponds to what percentile? So we want to know what's the percentile rank of 6. So if you look at the algorithm, and that's on the bottom of page 19 in your notes, the percentile rank corresponding to a particular data value, you have to first count the number of values that are smaller than that value, add 0.5, divide by the sample size, and multiply by 100%. So the number of data values in the sorted set, which are less than 6, there's 4 of them. And actually you can see that here. 1, 2, 3, 4. There are 4 values, but again, I'm recommending that you sort the set first and not look at the data set, because it can be confusing to do it that way. So there's 4 values that are less than 6 in the sorted set, and then we're adding 0.5, so that gives us 4.5. 4.5 divided by 16 is this value here, so 6 is approximately the 28th percentile. What are the bounds for detecting a possible outlier? So there's really 2 ways you could do this question. We have what's called resistant measures and non-resistant measures. In the resistant measures, those measures use IQR. The non-resistant measures would be those using 2 standard deviations away from the mean. So those values really are best used for data that is approximately bell-shaped. For the moment, we're going to look at resistant measures for this. So if you do the one variable stats, you can see, if you scroll down on one variable stats, in one variable stats you get the mean and the standard deviation, the sample size, the sum of the values, the sum of the scores, and so on. But if you use the down arrow and scroll down, you also find out the min, max, and the 3 quartiles. So the IQR is the interquartile range, and you have to take Q3 minus Q1. So Q3 minus Q1 is 12. So the lower bound for detecting an outlier is the Q1, which is 5.5, minus 1.5 times the IQR. So that gives negative 12.5. The upper bound for detecting a possible outlier is Q3, which in this case is 17.5, plus 1.5 times IQR, which is 35. So any values that are outside of these bounds are potential outliers. So if you look at the data set, there are no values outside of these bounds. So there are no potential outliers in this data set using these resistant measures. Now, if we had a new data set, since we just did this, and it gives you an idea of how useful these resistant measures are, the new data set just changed a single value. So instead of the maximum being 20 in the data set, the maximum is now 50. So if we answered the questions above using the new data, what do you think would happen? Well, you can see it here. The 60th percentile, same. 28th percentile, or the percentile ranking of 6, still the 28th percentile. Those things don't change. But in terms of potential outliers, the upper and lower bound for possible outliers, is still the same range that we said before. The only thing that would be different, the max changed, and the max is no longer in this range. So that would make our new max the potential outlier. So the 5-number summary, we've mentioned this earlier in class. The 5-number summary for a data set are the 5 numbers that you saw before, that I had before on the screen from your calculator. It's the min, Q1, Q2, Q3, and the max. These are the 5-number summaries, and with the 5-number summaries, those are used to construct a box plot. And we've made these before in class. We made them in R. You can't make them in Excel because Excel does not have a box plot function. Not in older versions of Excel. It's possible in the newest version of Excel they have one now. I'm actually not sure about that because I'm not using the newest version of Excel. But in, the version of Excel we're using in class I don't think is the newest version. We'll have to check that out. But as far as I know, Excel does not make a box plot. So the box plot, if you draw a number line, so you have to draw box plots to scale. Scale is important in box plots because what you're doing is you're just identifying 5 numbers. The min, the max, which should actually be over here, so sorry about that. The max is this value here on the real number line. And then the 3 numbers, Q1, Q2, the median, and Q3, which is here. So I can see your notes, it's a little messed up. But so this line here corresponds to the median of the data set. This line here corresponds to, whoopsies, Q3 of the data set. I have to go back one. And then this point here corresponds to the maximum of the data set. So those 5 numbers are relevant to make the box plot. The height of the box is irrelevant, doesn't matter at all. Okay, and so the Q1, Q2, Q3 form the box, and then the so-called whiskers of the box are the min and the max. So the shape of the box plot gives you a sense of the distribution of the data. So you could take a look at this. If you have bell-shaped data, you expect a symmetric box in the center, and these distances from Q2 to Q1 or Q3, those should be the same distances, right? Because of the symmetry, and then these are longer, like from the median to the max, and from the median to the min. Those are longer than, say, from Q2 to Q3 or Q2 to Q1. Okay, so this is approximately like what a symmetric bell-shaped data set should look like, and we'll see this throughout the semester. We'll be comparing box plots and histograms with shapes of data to get a better feel for this, to get a good feel for this. So remember the serial data? We did this in class. This is from StatCrunch. It's not as nice as the box plots we made in, I'm not sure if we made them in R, actually. I know we made the histogram in R. I'm not sure if we made the box plot in R. But, so here's the sugar content for those cereals. Here's the adult sugar, and here's the child sugar, and these are, on the same scale. And, you can see the difference in the distribution of the data by looking at this the box plots. You can see like 75% of the children's cereal, so that would go from Q1 to max. 75% of the children's cereal have sugar contents that's above, 10 grams of cereal or more, whereas for the adult data set, 75% of the data has less than 10 grams of sugar. So these boxes contains 50% of the data. You can see there's no overlap there. So the 50%, most adult cereals contain less than 10 grams, whereas most children's cereals contain more than 10 grams of sugar. Okay, so the rest of your notes, you have instructions for how to do things in the calculator, and I leave you to look at that as you need it.